My research on high-resolution imaging applies in a couple of domains of security. First of all, for example, in luggage inspection systems or package inspection systems. High-resolution subsurface imaging allows me to get sharp images of objects that would otherwise be difficult to separate. For example, in underground imaging, we would get sharp images of buried plastic landmines and allow us to use the shape of those images to determine the nature of the object that's there. In addition, I work on detection and classification of objects when the signals are buried amidst a lot of clutter. This allows me to do detection of small traces of chemical particulates that are present associated with the exterior of a package and allows me to determine the potential presence of explosives within it. This video shows a 3D reconstruction of the contents of luggage as generated by an analogic dual energy X-ray scanner. This is typical of portal detection systems. Now notice as the luggage rotates that the underlying explosives that's beneath the briefcase can barely be seen except from several angles. Fortunately, by fusing the information from the dual energy sources, we're able to get indicators of atomic mass number of the contents. Subsequent image processing and object detection can identify the extent of the material, i.e. the red sheet that's highlighted in the video. Future generations of portal systems will include additional sources of information. For instance, research is ongoing on the development of terahertz spectral imagers that could also look inside of luggage and give additional indications of the types of materials that would correspond to explosives. This video illustrates the problem of standoff detection. It shows a crowd of people walking towards a network of sensors. At a far distance, we have a radar sensor that can monitor whether people are carrying metal, and in particular, we're looking for metal bars that could correspond to pipe bombs. We see that the radar detects potential pipe bombs presence in some people and green flags appear on them in the video. As the people walk towards where we have other sensors, the wedges that you'll see on the video indicate the presence of a terahertz scanner and as well as an X-ray scanner, the little thin line that appears. This video illustrates the complexity of standoff detection systems. This is actually a simple scenario. Imagine a crowded city street or a shopping mall. In order to address such problems, we're going to need sensors that are able to uniquely track which individuals we detect have potential threats on them and be able to maintain continuity of track on those individuals so we know it's the same individuals that we saw before when they come in the neighborhood of other sources of information such as our terahertz imagers. The biggest fundamental problem in detection is that we must have systems that have nearly perfect detection. What I mean by that is they have a sensitivity that's nearly perfect and also a specificity that's nearly perfect. Sensitivity means that if something's there, we're going to detect it. Specificity means that if something is not there, we're not likely to declare a false alarm. This is extremely challenging and far from our current capabilities, but the costs associated with a false alarm are intolerable. Imagine if we were inspecting packages in the post office and every time there's a false alarm we had to open the package to inspect the contents. It'd be very expensive from a human cost as well as difficult. However, the cost of missing the presence of a threat would be even more so. So therefore that pushes us to design detection systems that have near perfect performance.